All right, getting into our lesson on geometric sequences. Again, we're just looking at another formula here, but similar to arithmetic sequences, these just follow a certain pattern. And there's always a formula or two we can apply to these. So a quick look at the formulas again that we're using for this unit are these five right here. And so we're kind of now into this stage. So we dealt with these two formulas when we have arithmetic sequences. But we're now looking at these two formulas when doing geometric sequences. So the one we're going to focus on in this lesson is the nth term, or used to find a general rule, but usually for specifics is what we use the u of n for. So again, we have u of 1 representing the first term of the sequence. R is going to be the common ratio, and we're going to talk about that here in a second. And then n would be the term number, so the 5th term or the 20th term, something like that. Connection that we always want to make on these, and it was the same when we dealt with this formula here, is simply that whatever u of n is, this represents the value of this nth term. So if we said something like the 10th term is 50, then n would be a 10 because it's the 10th term, and its value would be 50, and so that would be the u of n. But anyway, that's the idea that we're looking at for this lesson. So coming back to this, so geometric sequences are simply a sequence where you are always multiplying by some number to get the next term in the sequence. And that value is what we call the common ratio. So as you take a look at this sequence that we're seeing here, can we recognize that it's geometric? Yes, because I can tell that I am always multiplying by 3 to get the next term in the sequence. And so the 3 that we are multiplying by represents what we call the common ratio. So that's the R value within our formula that we're looking at here. So you're going to see this as U1 instead of A. Some books use the A, some books use the U1. So you'll see this as U of 1, the first term, and the common ratio. So we have the common ratio, which is 3. As far as just recognizing a common ratio, again, some patterns are harder than others to recognize. This is obviously 3. But as you start getting into maybe negatives or fractions or decimals, that can be tougher to do. So the easiest way to recognize a common ratio is, as we're looking at multiplying to the right, you can just work backwards and divide to the left. And so if I ever take any term and divide by the previous term, I should get the common ratio. So I could do that with 6 divided by 2. I could do that with 18 divided by 6. Any term divided by its previous term would give me the common ratio. So as far as just setting up something called a general term, if we just sub in into the formula right here, if I just sub in the first term of the sequence for U1 and the common ratio, or the R value, right here, which was 3, and we're going to leave n as n for now just because it's a general term, so this is supposed to represent any term. So this would be sort of the scenario for the general term. But we can now use this to find a specific term. So for example, if I wanted to now find or figure out what is the 13th term in the sequence, well, I can just sub in a 13 for n, and then the rest is calculator work to get the value of the 13th term. Same thing I mentioned with arithmetic sequences. You can do things like this without a formula. Like, you wouldn't need to know this formula in order to get the 13th term. You could just continue on the pattern, times 3, times 3, times 3, until you landed on the 13th term. But formulas are always about efficiency. It's a quicker way of doing things, especially when you get into bigger terms. This process becomes a lot quicker. So moving on to example 2. So here's another case where we have a geometric sequence. And so you take a look at the pattern. So here we have a little bit of a more difficult pattern to deal with. And so here's a case where some formulas would really help out. So as far as finding the 8th term, so in order to do that, remember what we need to know. We need to know the first term. We need to know the common ratio. And then we're going to be putting an 8 right here because we want the 8th term. And so as far as getting the first term, well, that's easy. We know the first term is 1/2. So that can go in. We know for the exponent, we're going to have 8 minus 1, so we're going to do this to the 7th power. But as far as the common ratio goes, this one is a little less obvious as far as what we're doing to get the next term, or what we are multiplying to get the next term. So here's a case where I would do, let's just take a term, like the second term, and divide it by the previous term in order to figure out the common ratio. So if we did negative 1/3 divided by a half, or you could say multiplying by 2 over 1, right? Multiply by the reciprocal. The result would be your common ratio. And so that's the easier way of figuring out the common ratio instead of just trying to figure it out just by looking at the numbers. So we put the common ratio in there. The rest is going to be calculator work. Be in the habit of using fractions instead of decimals for these. So remember, we have our calculator has a way of doing that for us. So I would say if you're watching the video for the first time, take a practice run at this with your calculator and make sure you can come up with this version of the answer. For the third example, in this case, they're again looking for a specific term, but they're providing us information in a different way. Instead of showing us the sequence like we got up above, they're just giving us a couple specific terms, and we are to use that information to then figure out what the 10th term in the sequence would be. So for this one, we know the 5th term is 3, and we know the 7th term is 3/4 or 0.75, and we got to take that information and come up with the 10th term in the sequence. Same formula. I'm still looking at this same setup right here. I still need to know the first term. I still need to know the common ratio, and we'll be putting a 10 right here since we're looking for the 10th term. But I got to come up with my two unknowns first. So we got to come up with a first term and a common ratio to do this. Keep in mind, something that we dealt with back in our very first unit of the year was dealing with a system of equations. A system of equations is needed whenever you have two unknowns. So in this case, I have two unknowns. I don't know the first term, the u of 1. I also don't know the common ratio. So if I had two unknowns, that means I need two equations, and I need to solve that system of equations. So looking at these, we're going to use this for one equation. So we're going to plug in a value of 3 when I have a 5th term. So 5 minus 1 is going to be the exponent. Notice I have two unknowns. I don't know the first term or the common ratio, so we're going to leave those as variables for now. And then we'll use this information to set up our second equation. So I know the 7th term is 0.75. So I have a value of 0.75. In my exponent, I did 7 minus 1 because I have the 7th term. So those are our two equations that we have, and now we have to solve these. When it comes to geometric sequences, you cannot use elimination to solve your system because of the exponents, so we have to use substitution instead. If you look over here at this formula that we have set up right here, I'm going to divide r to the 4th over to the left so that I can get u1 by itself, the first term by itself, so that I can then use this to substitute into my other equation. So if I know that u1 is equal to 3 over r to the 4th, then I can then sub in 3 over r to the 4th in for u into my other equation. And so I'm going to get this scenario right here by that substitution. When it comes to division, we know the rule is to subtract exponents. So that brings me to this scenario right here. I can then divide the 3 to both sides. Anytime you take the square root of both sides of the equation, we know to throw in a plus or minus. So I divided over the 3, I then square rooted both sides and came out with this result right here. So we have an interesting case on this because we don't know if the common ratio is a positive 1/2 or a negative 1/2. So we have to consider both scenarios. In either case, when I plug this back in for r in order to figure out what my first term is, so let's just say we're going to take positive or negative 0.5 and sub it back in right here in order to get the first term. Well, because I'm raising it to an even power, I'm going to get a positive result no matter which value I sub in. So I don't have two first terms, even though I have two potential common ratios, right? I'm going to get 48 as my answer for my first term, whether I use a positive 0.5 or a negative 0.5 for r. But we've come up with our two unknowns, so now I can simply sub those into our formula that we have right here in order to figure out the 10th term in the sequence. So we sub in the first term for u of 1, we have two potential common ratios that we're going to consider. We were looking for the 10th term, so we have 10 minus 1 as the exponent, and then the rest is calculator work. But notice we did identify two potential values for the 10th term. We didn't know if we were using a positive or a negative, so we do have two potential 10th terms. There is another way of looking at this. I sort of stopped showing this version about 2 years ago because students just were not catching on to how this worked. This is one we're going to overlook. This is a great approach to this type of a problem, and it tends to work for more people. So we're going to stick with that process right here. A couple word problems that we're going to have to be able to deal with when we do geometric sequences. So take a look at this one. We have a car worth $34,000, brand new. However, over time, it's going to lose 15% of its value every year. So as far as just coming up with a general rule to show what this would represent, well, one thing we want to point out is anytime we are increasing or decreasing by a percent, that always makes it geometric, right? Because it's not going to be losing the exact same amount every year, which is what arithmetic would do. It's losing a percent of its value every year, so it would be geometric. All right, it's going to have that geometric decrease that we're going to see on this. So as far as just writing the rule, this one's a little tricky, but again, consider the formula from up above. We have the initial value, or the first term in the sequence, is its original value, $34,000. The rate that it changes at is a little tougher to see. If it's losing 15% of its value every year, that means next year its rate would be 85% of its previous value. So, and that's something we'll deal with a little more in class, but that's the main idea here. If it's losing 15%, they could have just as easily worded this by saying it is worth 85% of its previous value. And so that's the way we have to view the common ratio for this in order to see what it would be worth next year or any other year. And then we're going to keep this general for now just because it represents the general term. So find the value after 6 years. So here's something that we run into as sort of a confusing issue within this chapter, is how do we identify the exponent for this? Because the tendency, because of the n minus 1, the tendency is going to be to put a 6 right here and say it's 6 minus 1, and so people are really going to want to put a power of 5 on this. The best way to view the exponent when it comes to geometric sequences, the best way to view this is completed periods of time. So when they say the value after 6 years, you got to see this as we are now at the beginning of the 7th year. And so we are now into the 7th term of the sequence, and so we have a 7 minus 1 for this right here. Again, if we're talking about completed periods of time, if we said after 6 years, that means we have completed 6 full years of time. And so we've completed 6 full years, which is why our exponent is a 6. Again, the other way to view that in terms of the minus 1 is to say, well, after 6 years, I am now in the start of the 7th year. And so if I am the start of the 7th year, I would do 7 minus 1 to figure out my exponent. So here's its value. After 6 years, or at the start of the 7th year, would be its value. How many years until the value falls below 10 grand? So remember, this car started out as being worth 34 grand, but every year it's decreasing in value. So at some point, it's going to fall below $10,000 if we continue on with this rate. So here's the setup that we're looking at. We now know the future amount of 10 grand. It's starting at 34 grand. Here's our rate of decrease. And we're trying to figure out how many years. So remember, the n represents completed periods of time. So that's what we're going to identify that as. If we sub in, here is the algebraic approach to this. I'm going to show you the calculator approach as well. So initially, to start this out, we would divide the 34,000 over to the left. So here's what you would see in the next stage. Because you are solving for an exponent, that always means logarithms. So in this case, I'm going to take this exponential form and rewrite it into log form. And so by putting something into log form, that's what gets the exponent by itself algebraically. So by changing forms, we went from exponent form into log form. That always isolates your exponent on the other side. And this can now go in your calculator. So I'm going to remind you really quick of how we can do that in our calculator. So I have the log 0.8 base of 0.85 and then of 10 over 3/4. So 34. So let me show you real quick how you could do that in a calculator. One of the cool features on here is if you go under math, go down to the option that says log base, and we can literally just type that in. So I can put in the 0.85. Right here I can put in the 10 over 34 and just hit enter. And we have our answer. So that's one way of coming up with the answer that you see here directly from the calculator. Another option is to use the graphing method. Oftentimes students struggle with logarithms and they'd rather not go to this and they want a different way to solve. So there is a different way to solve. So I'm going to show you how to do that. But the way we've learned it in the past, and we will have already taught this year, is to graph 10 over 34 as one equation, 0.85 to the n as a second equation, and simply we want to find out on the graph where those two guys intersect or where they are equal. So we're going to go to our y equals, and let me show you how to do that on the calculator here. So if we go over to the calculator, so I'm going to go to my y equals, and I have 10 over 34 as one equation. I have 0.85 raised to the x as my other equation, and I'm simply going to hit graph. And my solution is just going to be wherever those two graphs intersect. This is one of those cases where the one challenge of the graphing method is you have to sort of adjust your window sometimes to fit the graph. These graphs might intersect way over here, and you wouldn't see it on your screen, and so you might have to toy with the window a little bit to see where these guys intersect. Or the zoom feature can help as well. It looks like they're intersecting about here, so I'm going to zoom, and I'm going to choose zoom in, enter. I'm going to go to the area of the graph where I want my calculator to zoom in on. So I'm going to put my cursor right about there and hit enter, and so that my calculator will zoom in on that area of the graph. But now I can see a little more clearly that there's a point of intersection right about there. So I'm going to go to calc, I'm going to choose intersect, and they're going to say, is this your first curve? Just hit enter. Is that your second curve? Just hit enter. Guess, enter, and there you go, 7.53. I get the same answer with the graphing method. So that's another approach instead of logarithms that we can also use. Anyway, let's finish this off. So remember what we've talked about a second ago as far as how we understand the exponents within a geometric sequence. They represent completed periods of time. So let's see if we can make sense out of what this would mean. If this is falling 15% per year, that means it would take about 7.5 years in order for the value of the car to go below 10 grand. If we were talking about just years, right, not in between years, but pure completed periods of time, just full years, that means this would happen in the 8th year. So remember, if this is 7.5 years, that means we've completed 7 full years, and we are now halfway into the 8th year. So there's a couple ways we could word this. We could either say, we could leave it as the decimal and just say it would take 7.53 years, or we can understand this as occurring in the 8th year. So there's kind of two ways you could look at that, and they would both mean the same thing. So this is occurring somewhere in the 8th year, again, because it's taken more than 7 full years to happen. And that's it.